Okay, let's talk about symmetries. In particular, we're going to talk about symmetries of figures. Now, symmetries are extremely important. Much of art and music depends on symmetry. Also, symmetry is of fundamental importance in physics. Many of the great breakthroughs in quantum physics are based on observations of symmetry. And in fact, symmetries can be used to predict the existence of new particles. So, symmetries, in fact, is the origin of group theory. The study of symmetries is where group theory came from. Okay, so let's go into definitions. Now, we're going to use this definition of symmetry. Symmetry of a geometrical figure is a rearrangement of the figure that, first of all, preserves distances and angles between points of the figure and leaves the appearance and location of the figure unchanged. Okay, let's do a simple example here according to this remark. Suppose I take 2 points A and B. All right, so here we have a segment. I can consider this segment as a geometrical figure. Okay, now suppose I pick up this segment and I flip it around 180 degrees, and then it will look like this. Okay. Now, if you didn't have the letters labeling the points, these two would look exactly the same. If I took this segment and you left the room and I flipped it and you came back, you couldn't tell I'd done anything. The motion is rigid, so the distance between A and B hasn't changed. It's just that their location has changed. Now, on the other hand, if I had 3 points arranged in an angle like this, A, B, C, if I took this angle figure and you left the room and I consider this axis, if I took it and flipped it around this axis going out of the page and flipped it around so that the A is no longer A but C and the C is no longer C but A, and you came back, you wouldn't know that anything had changed. But you see the angle has been preserved. The angle started this way, and when I finished the flipping, it was still this way. So angles and distances are preserved. And in fact, mathematically, you only need to say the distances are preserved, and that implies the angles are preserved, but that's beyond what we're going to talk about right now. So here's an example of an object that has, we say objects that have symmetries have some kind of symmetry. Now I could take this Mercedes logo and rotate it counterclockwise 120 degrees, and it would look the same. Okay? I could rotate it 240 degrees, or I could flip it around this axis, or this axis, or this axis. Any one of those rigid motions would not change the appearance of the logo. So all of those motions are called symmetries. Now, we don't say that translations are symmetries. Translation means that you move this object up or down like I'm doing right now. If I move it back and forth, that's called a translation. But you can see that even though the shape has not changed, the appearance has changed because the location has changed. So we don't call these shifts or translations, we don't call those symmetries. You also have an identity symmetry that does nothing. Now, if you look at this picture, this may remind you of the 6th roots of unity that we did in the complex plane. If you draw the complex plane like this, these are the positions of the 6th roots of unity. And if you have rotation, that A goes to B, B goes to C, C goes to D, D goes to E, E goes to F, etc. So you're moving the point that was at location of A to the location at B, the point that was at location of B to move to the location C. So you should think of A, B, C, D, E, F as labeling the locations. You shouldn't think of these locations as fixed on the figure. These locations are fixed and the figure moves around. Okay. So you can see that this is a function. I'm taking this point at this location A and moving it to the location of B. That's like mapping A to B, and map B to C, C to D, and so on. Okay, so here's a representation of my rotation. 60-degree rotation. A moves to B moves to C, etc. Okay. Now, in fact, since a symmetry is a function, we can ask the question whether or not it's a bijection. And in fact, it is a bijection because it does map the set. For instance, if you look in this case, it maps this set A, B, C, D, E, F, the set of locations to itself, the set of points to itself. So it's onto, because it maps F's all the way to itself, and it's one-to-one because two different points are going to map to two different resulting locations because the distance is preserved. If I have a non-zero distance between 2 points, then after the symmetry, that non-zero distance is preserved. So in this way, we get both onto and one-to-one for our mapping. Okay, so any symmetry is a bijection. But that's not true that every bijection is a symmetry, but every symmetry is a bijection. So you can, that's an exercise for you to think up some bijections that are not symmetries. All right, let's consider another geometrical figure, the rectangle. Now, the rectangle is not quite as symmetric as the hexagon, but it still does have symmetries. First, it has the trivial symmetry, where you map the rectangle to itself, don't move it at all. Second, it has 180-degree rotation if I take this and rotate it this way. Next, it has reflection about the vertical axis. So if I flip it this way around the vertical axis, that means that A would go to D and vice versa. B would go to C and vice versa. Or I could flip around the horizontal axis. Okay. All right, this one we're going to call SV, and this one we're going to call SH. Okay, and this one we're going to call R180. Okay. All right. Now again, we're going to draw on our knowledge of functions and consider the composition of symmetries. Now symmetries map a set S to itself, so it's natural to compose because the domain of the codomain of the function is the same as the domain. So I should be able to compose symmetries if they're all acting on the same function. So let's consider the composition of these two symmetries, the 180-degree rotation of a rectangle and the reflection about the vertical axis of the rectangle. All right, so we saw those two symmetries. R180 was this one here. You take this rectangle, rotate it around, and this one reflection, you go this way. So you want to see what happens if you do first one and then the other. Sorry, I went too far. Now this exercise takes you through. There's another way to do this in a more systematic way. If we represent symmetries in this way called Tableau Form. Right. Tableau Form means you list all the points on the figure, and then you list where they go on the second line. So if you remember R180, if you think of how this goes, A is going to go to the location of C, B goes to D, C goes to A, D goes to B. So A, B, C, D goes to D, C, A, B. Okay. Did I say that? A, B, C, D goes to C, D, A, B. Don't remember if I said that right. Okay, so let's see if that's what we have here. A, B, C, D goes to C, D, A, B. That means A goes to C, B goes to D, C goes to A, D goes to B. Now, if you consider the flip around the vertical axis, this is the representation of that in pairs. Remember here, this was A, this was D, this was B, this was C. And remember, A and D switched and B and C switched. So A goes to D, B goes to C, C goes to B, D goes to A. So you would represent this as A, B, C, D on the top row. On the second row, A goes to D, B goes to C, C goes to B, D goes to A. Okay. All right. Now suppose we want to find the composition of 180-degree rotation following the vertical flip. Okay. Remember, when you write function composition like this, this is the function that's applied first because you can think of x here. This is the function that's applied first, and this is the function that's applied second. Right. Now here's the Tableau representation of R180, and this is the Tableau representation of the flip around the vertical axis. Now you can follow this verbal description, but you can also see from here. I want to know where A goes as a result of the composition of these two functions. Well, A goes to the position of D according to the vertical flip. But then the rotation takes D to the position of B. So altogether that's giving me A goes to B. Right? A goes to D, the D goes up here, D goes to B. Okay, so A goes to B. Where does B go? B under the vertical flip goes to C, but this flip goes here, and that goes to A. So I get B goes to A. C under the vertical axis flip goes to B, but B goes to D. So that gives me C goes to D. Now naturally we should get D goes to C. Let's see if that works out. D goes to A goes to C, D goes to C. And if you draw the picture, you can see what this corresponds to. This actually corresponds to a different symmetry. If we have A, B, C, D here, A goes to B, B goes to A. These two are exchanged. These two are exchanged. That we've gotten, by magic, the flip around the horizontal axis. So flip around vertical axis followed by 120-degree rotation gives me the flip around the horizontal axis. Pretty cool. So you might wonder, is a symmetry composed with symmetry always a symmetry? And in fact it is. You'll see some exercises. And you can prove that. And it stands to reason that if each one of these functions both preserves is one-to-one and onto, preserves distances and angles, then the composition will also preserve distances and angles. Okay, some more exercises about what to do with these symmetries. All right, so now we reach a big question. Do symmetries form a group? We'll talk about that in the next video.